Okay, I hope everybody is home and keeping safe in these difficult times. I'm going to go through a series of videos with you here to just get you up to date on quadratic functions and hopefully move on to cubic functions and beyond if we need to. So once you've watched the videos, any questions, please email me, leave a message in Google Classroom, attempt the questions in the exercise as mentioned, and if there's any issues then we can look at alternatives. Alright, so first things I'm going to be looking at is the basics of a quadratic function. All quadratic functions are in the format y equals ax squared plus bx plus c. Now we already know from algebra that c is the y-intercept, the point at which the quadratic function crosses the y-axis. A is a new one to us. So A tells us two things. Firstly, it tells us whether it is a u-shaped or n-shaped function. So where we have value of a that is greater than 0, in other words, a positive quadratic function, that means that the shape is going to be a u-shaped function. So this will have a minimum turning point and it will cross the x-axis a number of times depending on the determinant. If we have a value of a that is less than 0, in other words, a negative quadratic, that means we are dealing with an n-shaped function. So that's our basics. So the other thing that a tells us is how wide or narrow a quadratic function is. So for that we look at the absolute value of a, and if the absolute value of a is less than 1, in other words, if we're looking at a fractional value of a, for example, a half, 2/3, or anything like that, then we are looking at a wide graph. I'll explain what I mean by this in a second. And if we are looking at an absolute value of a that is greater than 1, we are looking at a narrow graph. So let's look at a few examples. So our normal x squared graph, so if we're looking at the graph y equals x squared, that goes through the origin, the point 0, 0, and we have a u-shaped curve which is perfectly symmetrical. Worth noting here that the y-axis is actually the axis of symmetry of this graph as well, meaning that it occurs down the midline of the function. Now let's look at the graph y equals a half x squared, and it'll explain what I mentioned here. So if y is equal to half x squared, we are looking at a graph that is wider. It still goes through the origin because the c value, the y-intercept, is 0, but again perfectly symmetrical, but the arms are wider. Then if we look at the graph y is equal to 2x squared, we are looking at a narrower graph. Still goes through the origin, still perfectly symmetrical, but narrower graph. So you can see the value of a affects the shape and also how wide or narrow the graph is. All right, we also know that c is the y-intercept. So those are our basics. Now what we're going to look at in this video is finding the maximum or minimum turning point of a quadratic function. Now there's a number of different ways we can do this. We're going to stick to two methods at the moment. We learn a further method in the later chapter of differentiation, but for now, so finding the maximum or minimum turning point. So let's look at method 1. So remember, in our quadratic function ax squared plus bx plus c, to get the minimum turning point or maximum turning point, so we'll have a minimum turning point on a u-shaped function and a maximum turning point on an n-shaped function. So to get the x coordinate of this turning point, we use the formula x is equal to minus b over 2a. All you need to do is take the numbers, the coefficients of x and x squared, and fill them into this formula. That's our x coordinate. To get the y coordinate then, we look at sub in the x value. So let's look at an example. All right, if we have the function y is equal to 2x squared plus 8x minus 3, all right? We're dealing with a positive quadratic, which means that we're looking at a minimum turning point, and according to this method here, the x coordinate of the minimum turning point minus b over 2a is going to be minus 8 over 2 times by 2, which gives us minus 2. All right, so this here is the x coordinate of our turning point of our quadratic function. To get the y-coordinate, we're going to sub -2 into the original function. And from that, we get -11. So we're looking at a minimum turning point of -2, -11. We also know that it cuts the y-axis, at -3, and then to figure out the x-coordinates, the x-intercepts, you'd have to solve the function, let it equal to 0 and solve. That we've covered already. So that's method number 1. Fairly straightforward. You just have to remember your formula of -b/2a. Now let's look at method 2. Method 2 we've actually come across already, and it is completing the square. So if we were to complete the square, so we're starting off with our function y is equal to 2x squared plus 8x minus 3. So remember, when we are completing the square, we can only deal with a single x squared coefficient. So first of all, we must factorize out the x squared, so x squared plus 4x minus 3 over 2. And then we have to take the coefficient of x, we half it, square it, add it, then subtract it. So half of 4 is 2, so in after the x there, we're going to have 4x. So we have half of 4 is 2, 2 squared is 4, we add 4, subtract 4, and then we have the remainder of our function. So tidying it up, we have x squared plus 4x plus 4, which forms our perfect square. Minus 4 minus 3 over 2 gives us minus 11 over 2. Factorizing this, we have x plus 2 to be squared, and fully simplifying it, in other words multiplying in the 2, we have 2 bracket x plus 2 to be squared minus 11. Now remember, this number out here is not going to affect the turning point of the function. What this number does, it tells us how wide or narrow. This is the value of a. So that is going to dictate the width or breadth of the function. So from this, when we're determining a turning point coordinate from completing the square, we take the number in the bracket, that forms our x coordinate, but we must remember to change the sign. So the minimum turning point in this case, we change the sign of the x number, so that becomes a minus 2. Keep the sign of the y coordinate, that stays as minus 11, and you can see here we get the same answer. All right, so those are our two methods for finding the maximum and minimum turning point. All right, now based on this, we also have to note that there is an axis of symmetry. Now, the axis of symmetry of a quadratic function. So if, for example, we look at a quadratic function, the axis of symmetry is the vertical line that splits the quadratic function graph into two equal halves. The interesting thing is that this coordinate here is going to be the turning point of our quadratic function. So if we look at the function 2x squared plus 8x minus 3, then we know that the equation of the axis of symmetry would be based on the x coordinate, so it would be x is equal to minus 2. All right, so that would be your equation of your vertical line. So your axis of symmetry cuts the quadratic function into two equal halves, and it is based on the x coordinate of the turning point. Quickly, it's minus b/2a if you have the value of the function. All right, so other things to note on our basics of quadratic functions that we've come across already. Just to find the x coordinate, if you're drawing the graph of a function, which you'll be doing in exercise 9 based on this video, the determinant b squared minus 4ac tells us how many roots the quadratic function has. So remember, if b squared minus 4ac is greater than 0, it has 2 real roots. B squared minus 4ac is equal to 0, 1 real root, and b squared minus 4ac is less than 0, no real roots. Okay, so based on that, now I would like you to do questions, do a few out of questions 1 to 4 on page 390. And if you have any questions, please let me know.